Okay, so hi. Um, week two, in week two, basically what sir covered was in the first lecture. There was some tight binding model uh, part that was covered, as in how to write tight binding models in terms of second quantization. Let me write it down. Then what he followed with it was just some examples wherein you can use second quantization methods to solve certain kinds of models. So a standard transformation, the Jordan-Wigner transformation, is used to solve spin models. Basically, we convert it to fermionic models, and then we can go ahead and solve it. Um, then he spoke about ferromagnetism. Okay, and finally, again, it was singlet and triplet states in Hubbard models. So we also basically the description of ferromagnetism was using Hubbard model, but here in ferromagnetism he also taught about the transfer matrix method. Okay, so this was the brief outline of what happened. Actually, the reason why I'm showing this is in the assignment, what I see is there are certain topics, as in the fifth question and the fourth question of the assignment, is based on lectures which are going to be covered in the next week, in week three. So, uh, my preference is that I would rather not want to go into those questions for the simple reason that my job is not to make you solve the assignment. My job is to make you understand the concepts and do give you a little practice of it. Okay, so I would rather cover certain topics which are in these lectures rather than the ones in the next lecture, next week, because in the next week lecture I will be covering the topics which are covered in the next week. So I'll focus on the topics which are covered in this week itself. Okay, so that's my idea, and let's do something about the tight binding model first. Okay, we already did something about the tight binding model last time, but I told you the graphene problem as homework. So today we'll explicitly look at the graphene problem. Okay, so okay, suppose we have uh, a lattice like this. Okay, so as I said last time, there are two kinds of atoms in this lattice, right? Let me mark one kind as with, sorry, with red dots. All of these atoms are of the same kind, the ones I'm marking with red dots. Okay, and then I'll mark the second kind with yellow dots. The lattice vectors are of this form. Okay, you can take this as your lattice vector or something else, but the uh, lattice vector, what you'll end up getting will be the same. Basically, you can either join two red atoms, that will be called your lattice vector, or you can join the midpoints of these lines. Suppose I consider, wait, this went away. Okay, suppose I consider this. as my unit cell. Okay, then all of these are my unit cells, and the center of this unit cell lies here, the center of this unit cell lies here. So I can also draw a vector joining these two. Okay, and this has to be called my lattice vector. And let's say there is another unit cell here, so this is my second lattice vector. My point is that these two lattice vectors would be equivalent to these two lattice vectors in blue which I'm drawing. They are equivalent. So basically you either join the red dots, you join the blue yellow dots, or you can join the midpoints of the unit cells. Eventually what you end up getting is the same. Okay, so the blue lines are way more convenient to use, that's why we'll rather use them. And I mark the unit cells, so these are the unit cells. Okay, so now let's start writing the Hamiltonian in the second quantized notations. So as we already know that we are supposed to consider these hoppings, right? And again we'll be considering only the nearest neighbor hoppings, because that's the best approximation that we have. Okay, that's the first order of approximation that we take. All right, so what will we do? I need to consider unit cell and show all its hoppings, right? So for that I want all the hoppings present for a particular unit cell. Okay, so I will consider this unit cell itself. Okay, yes, this is my unit cell, and I want to consider all the hoppings from the red atom and the yellow atom. Okay, I hope you understand why I have taken this as the unit cell, because there are two different kinds of atoms. So uh, you have studied in tight binding model that when you have a unit cell which contains two different kinds of atoms, so this is how you have to deal with. You have to take both the atoms as one unit cell, and translating this unit cell along the lattice vectors gives me the entire lattice. So that's why it's a two atom unit cell, and that is why I'm considering this. And now I have to talk about all kinds of hoppings within this. Okay, so sum over, and I'll take I basically is the index of all the unit cells. So I'm taking sum over I means I'm taking a sum over all possible unit cells. Okay, so sum over I, um, let me call this unit cell A, unit cell B, unit cell C, unit cell D. Okay, so the purple unit cell is going to be hopping across all these pinkish unit cells. The atoms in the purple unit cell will be hopping to these particular unit cells. Okay, so the first term is from the red atom, this is the hopping that I'm considering. So Ci dagger Ca. So basically my particle is coming from A to I. Okay, from the yellow atom at A to the red atom at I. Plus I'll consider this hopping Ci dagger Cb. Plus I'll consider this hopping this is within the unit cell, right? Because the yellow atom lies within the unit cell. So this hopping is within the unit cell. Now from the yellow atom, Ci dagger Cc plus Ci dagger Ct. Plus Hermitian conjugate of all these hoppings. So this is my entire Hamiltonian in the R space. Now if I take a Fourier transform to take it to K space, what I end up getting is sum over I, sum over K, K prime, Ck dagger, Ck prime, e raised to the power of I, Ri dot K, e raised to the power minus I, Ra dot K prime. Oh, by the way, there is also T. T is the hopping constant, of course. So similarly, I'll write it for the other terms as well. Ck dagger, Ck prime, e raised to the power of I, R I dot K, e raised to the minus I, Rb dot K prime, plus Ck dagger Ck. The K minus K prime will go away for this case. So there will be only, or maybe I'll do it just to show you, my Ri K minus K prime. Right. Plus Ck dagger Ck prime, e raised to the power of I, Ri dot K minus Rc dot K prime. K prime is important, of course. Ck dagger Ck prime, e raised to the power I, Ri dot K minus Rd dot K prime. Okay, so these are my terms. Now we need to get involved with the geometry. So Ra, what is Ra? Basically Ra, if I am taking the lattice vectors from the red points in every unit cell to the other red point in the next unit cell, if these are my lattice vectors, then Ra is basically the position vector for this point, because this is the red one, right? This is the yellow, this is the red, this is the red here. Let me join it with black so that you are clear of what I'm saying. So Ra is basically the position vector. Ra is basically the position vector of this point. Rb is the position vector of this point. Okay. I can also write the position vector of this point as Ri, which is the position vector of this point, and then plus the lattice vector. Right? I hope that makes sense. Similarly, I can write the Rb as Ri plus the second lattice vector. Okay, so let me show it to you how it's done. Ri plus the lattice vector. And what is this lattice vector? So we'll have to calculate this. This is, let's say, the distance between the nearest neighbor carbon atoms in graphene is A. Okay, so this is 120 degrees. The interior angle is 120 degrees. So how much is this? This is going to be 30 degrees. 120, 30, 30, which gives me 180. So this is 30 degrees. So I'm just writing down the coordinates for, let's say, A1 and A2. So A1 has to be and A1 equals A cos 30 degrees plus A plus A sin 30 degrees j cap. That is A root 3 by 2 I cap plus sin 30 is, yeah, so 3A by 2 j cap. And A2 will simply be minus A root 3 by 2 I cap plus 3A by 2 j cap. I can clearly see that the j cap component is the same, I cap is only reversed. So that is going to be A2. So what I end up getting is, basically I know the forms of RA and RB now. And similarly, RC can be written as RI. RC can be written as what? RI minus what? Minus A1, right? RI minus A1, and RD can be written as RI minus A2. Because RC is this, so RI minus A1 and RD is RI minus A2, right? So this is what we end up getting. So what do we have now? Now h of k is equal to sum over I sum over k comma k prime c dagger k c k prime e raised to the power of, I need to remember writing down t, e raised to the power of what? I R I k minus k prime e raised to the power of minus I k prime A1 plus c k dagger c k prime e raised to the power I R I k minus k prime e raised to the power minus I k prime A2 plus c k dagger c k prime e raised to the power I R I k minus k prime plus c k dagger c k prime e raised to the power I R I k minus k prime e raised to the power of plus I k prime A1, because A1 has a negative sign here, that's why, plus c k dagger c k prime e raised to the power I R I k minus k prime e raised to the power of plus I k prime A2 plus Hermitian conjugate. So what do we end up getting? We end up getting, we can sum over I e raised to power I R I k minus k prime is equal to what? Delta of k prime. Therefore, actually there is a t by n also, because when I took a Fourier transform there is a t by n, so both these n's get cancelled, and what I end up getting is k बचता है, because delta k prime will remove k prime as well. So I end up getting K, C, K dagger, C, K. And what all do I have? 1 plus e raised to the power of minus I K A1 plus e raised to the power minus I K A2 plus e raised to the power I K A1 plus e raised to the power I K A2 plus this is what you end up getting. Oh, right. So, what I forgot was, because there are two kinds of atoms, so at least I have to mark them as uh, atom of kind A and atom of kind B. Basically, red and yellow, R and Y. R and Y. Basically, I have to mark them as R and Y also. So, what I end up getting is this K with an R and this K with a Y, because the hopping is between a red and a yellow atom. So e raised to power minus I K dot A1 plus e raised to power minus I K dot A2 plus there is also the hopping between yellow to red, and that will also have e raised to 1 plus e raised to power I K dot A1 plus e raised to power I K dot A2. This is the kind of Hamiltonian you end up getting. You have two different kinds of atoms. For those two different kinds of atoms, you have two different kinds of terms. Yeah, so for those two different kinds of atoms, you have two different kinds of terms. So this is a very important, crucial point to consider, that your CK daggers also have not just the lattice index but also the kind of atom, because the lattice index or I that we are considering is just a unit cell index. तो मैं जब सी आई डैगर बोल रहा हूँ तब मैंने ये नहीं बताया कि इट इज़ when I say CI dagger, I have not told you that whether the atom or the electron is being created in the red kind of lattice site or the yellow kind of lattice site. So I need to add a suffix R also. So that's an error which I need to rectify. Now this is yellow, R, yellow, red, and vice versa, and a Hermitian conjugate. But this term won't have a Hermitian conjugate because it's the same. So yeah, it's anyway covered. I just wrote it once, that's why. But these terms will have a Hermitian conjugate. So these terms technically also don't have a. So yeah, this is what it ends up being. So this is where we end up. Okay, this is what it is here. But very important that RY has to be considered, a crucial point. Here also red, yellow, red, yellow, red, yellow, yellow, red, yellow, red. Right, so this is red, yellow, plus I k dot a1 plus e raised to power I k dot a2. ठीक है? So yeah, this is exactly what we should end up getting. So basically then you can write your graphene Hamiltonian in this manner: ck dagger red, ck dagger yellow, 0 0 fk f star k ckr cky. ठीक है? So basically if you open up this matrix equation, you end up getting exactly these terms, and obviously this is h, but this is h of k. तो इनमें क्या फ़र्क है? What is the difference between these two? The difference between these two is that here I am showing a sum over k, so this is a complete Hamiltonian, whereas h of k is just the k dependent term which I have isolated, only one k dependent term which I am taking out. So h of k basically is just one term, just the Hamiltonian for any particular value of k. That is what you take out, and the full Hamiltonian requires a sum over k. The full Hamiltonian requires a sum over k. ठीक है? So this is the Hamiltonian you get. Now the question is that what you need to do is you want to expand it at k and k plus and k minus points. The assignment question, it says that find the nature of the dispersion in the vicinity of the Dirac points given by these numbers. So you get Dirac points basically by k plus and k minus. At k plus and k minus, plus minus 4 pi by 3 root 3 a comma 0. So this is my k plus and k minus. At these points we get the Dirac points, which means if I plot the dispersion of this particular band, they will be touching at exactly they will be touching each other at exactly these points. These are my Dirac points. तो पहले तो firstly, how do I derive this? How do I get this? For that I have to I'm just rewriting this. I normally have to solve the eigenvalue equation for this matrix, which will give me the band dispersion, right? So what do I end up getting? Basically it will be this matrix minus lambda I, मतलब minus lambda f of k f star of k lambda minus lambda. This is what we do, right? And we take a matrix of this, a determinant of this. It is already matrix. The determinant of this has to be equal to 0. That gives me the band dispersion, correct? Basically what I did is, in the diagonal I did minus lambda I. I took this matrix f of k f star of k 0 minus lambda into 1 0 0 1. Of course you know this method, I'm just elaborating if at all you are getting confused by how I've written it, but of course you know how to do this. I'm just trying to find the eigenvalue of this matrix. So how do I get the eigenvalue? Lambda square, this matrix I'm solving, lambda square minus fk f star of k equals 0. So lambda square minus, Now I need to find the value of f star of k. This is it, fk and f star of k. So multiply these two. 1 plus e raised to power minus I k dot a1 plus e raised to power minus I k dot a2 multiplied by 1 plus e raised to power I k dot a1 is e raised to power I k dot a2. This is equal to 0. So lambda square minus 1 plus e raised to power I k dot a1 plus e raised to power I k dot a2 plus e raised to power minus I k a1 plus 1 plus e raised to the power of minus I k dot a1 plus a2 plus e raised to power minus I k dot a2 plus e raised to the power of it's a2 plus a1 now it's a1 minus a2. Yeah, so this makes sense. Plus 1 is equal to 0. So lambda square minus of 3 plus, I have a few cosine terms, 3 plus 2 cosine k dot a1 plus 2 cosine of k dot a2 plus 2 cosine of k dot a1 minus a2 is equal to 0. Is that correct? a1 k2 this, yeah, I think that's correct. So then what does this end up becoming? k dot a1 क्या है? I already know a1 and a2. a1 is this. So k dot a1 will simply be this multiplied by kx and this multiplied by ky, because I'm taking a dot product, correct? So a root 3 kx by 2 plus 3a ky by 2 k dot a2 is equal to minus a root 3 kx by 2 plus 3a ky by 2, and k dot a1 minus a2 is equal to, a1 minus a2 will be what? a1 minus a2 will be a root 3 kx. The ky term will get cancelled off and I will end up having only kx term, and which will be double the kx term. a1 minus a2 is a root 3 kx. I hope there are no doubts. Therefore, lambda square minus 3 plus 2 cos a root 3 kx by 2 plus 3a ky by 2 plus 2 cos a root 3 kx by 2, sorry, minus a root 3 kx by 2 plus 3a ky by 2 plus 2 cos a root 3 kx equals 0. Now cos a plus cos b, so lambda square minus 3 plus 2 cos a plus cos b is 2 cos a plus b by 2. That's correct, right? So sin a minus sin b as 2 sin cos sine, but here for cos a plus cos b has both cosines, right? Yeah, so 2 cos a plus b by 2, which is 3a ky by 2 cos I have to subtract these two, so cos root 3 a ky by 2 kx, sorry, root 3 a kx by 2, which means this is just simply 4 cos of this plus 2 cos of a root 3 kx. So now let's see what this is. 4 pi, basically kx is equal to 4 pi by 3 root 3 a and ky equals 0. Let's check this. If I put kx is equal to 4 pi by 3 root 3 a, 4 pi by 3 root 3 a, here what I get is cos of root 3 a by 2 into 4 pi by 3 root 3 a. So a gets cancelled, root 3 gets cancelled. This is cosine of 2 pi by 3. What is cosine 2 pi by 3? Cosine 2 pi by 3 basically 120 degrees. Cos 120 degrees is equal to cos of 180 minus 60 degrees with a negative sign, because cosine in the second quadrant is negative with a negative sign. So is equal to minus of cos 60 degrees, which is minus half, right? So that gives me minus half. Ky is 0, so that gives me, this is 1, this is minus half, and this is minus half. So what does that give me? It gives me exactly 0, because 3 minus 3, यहाँ पे ये 3 और इसकी वजह से minus 3 मिलेगा, that gives me 0, so lambda becomes 0. So इसको solve करके basically you find the touching points. ये हमारा dispersion relation है. This is lambda square. Lambda square is this entire thing. Let me just remove all of this. I just wanted to show you by verifying that this equation will give me zeros at the Dirac points that have been described. Okay, so this equation itself has zeros exactly at Dirac points. So lambda square is this. So lambda को ये कर देते plus minus square root of 3 plus 4 cos 3a ky by 2 another cos root 3a kx by 2 plus 2 cos a root 3 kx. Oh, there is 4 pi by 3 here, which will be pi plus pi by 3. Yeah, even that is negative, minus half. So basically this is your dispersion relation. Okay, and you want, for Dirac points, you want this to be exactly equal to 0. So what we found out was, for this being exactly 0, wo jo k plus or k minus points, the ones which are given here, the k plus and k minus points, they exactly make the term inside the square root 0. You can check by substitution, but yeah, that's the idea. So this is how you get the dispersion. Now what you want is, you want to expand around the Dirac points and talk about the dispersion. How does the dispersion around the Dirac points look like? Okay, so now let's do that. Let's say I take the k plus point. Okay, what is k plus point? So now my k has a very definite value. It is k plus a small k. Let's write the small k as dk. No, dk has a very definite connotation. I don't write x. What do I write? P. Perfect. Yeah, that makes sense. So now basically the mod p tends to 0. I'm taking a very small vector p about k plus plus a very small vector around it, and I want to see how the dispersion looks like. That's the whole idea of Dirac dispersion. So lambda is equal to lambda of k is equal to plus minus square root of, I'll take only one sign, I'll take only, let's say, plus square root of 3 plus 4 cos 3a ky is 0. So but p is both px and py. Obviously p has both px I cap plus py j cap. So I'll have to expand this as well. Zero plus py by 2 cos of root 3 a by 2 kx plus px plus 2 cos a root 3 kx plus px. Okay, this is your expansion around k plus. You can do a similar thing around k minus as well, but I'm doing it around k plus. So 3 plus, now we know that cos ka expansion, let's say cos of x plus a. How can I carry out this expansion? Simply cos So that's equal to cosine of x plus minus a sine x, right? And I want to do a first order expansion, of course. So first order matlab, I want the order of p to be just linear and not p square or p cube. So we will take care of that, of course, when we are doing the expansion. So 4 cosine uh, 3apy is, I'll basically write a bracket here. So 4 cosine of 0 plus 4 minus py minus 4py into sine of 0, which is 0. Okay, so py is not contributing much, as we can see here. Now next, cos root 3 a by 2 kx, capital Kx, minus px because there is a derivative, so I have to also write inside terms, which is root 3a by 2 to root 3a by 2 sine of root 3a px by 2. Plus 2, and you have a cosine of a root 3 kx, k plus, sorry, why am I writing kx? This is k plus, minus px root 3a sine of root 3a px. I hope that's correct. What I have done is 3a by 2. Okay, so this entire thing is inside the square root. Yeah, so lambda of k, lambda of p actually is equal to what? Square root of 3 plus 4 cos root 3 a by 2 k plus 4, actually it's minus 4 px root 3a by 2 sine of root 3a px by 2 plus 2 cos plus 2 cos a root 3 k plus minus 2 px root 3a sine of root 3a px. Okay, and now 3, this term and this term, we know they together go to 0. That's the starting point. We have already seen that when I put 4 cos root 3a by 2 k plus, I get a minus 2 here. When I put it 2 cos a root 3 k plus, I get a minus 1, and that totally removes this. So I cancel out those 3 terms, and what I end up getting is minus 4 px to root 3a by 2 px sine of root 3a px by 2 minus 2 px minus, oh, so sorry, minus 2 root 3a px sine root 3a px. Now we know that sine a by a for limit a tending to 0 equals 1, which means at limit a tend to 0, sine of a can be approximately written as a itself. So therefore lambda of p becomes what? Square root of minus 4 root 3a by 2 px into root 3a px by 2 minus 2 root 3a px to root 3a px. This gets cancelled. Root 3 into root 3 gives me minus 3a square px square minus 6a square px square I think we have an overall sign problem somewhere. There has to be some kind of a minus sign or something. Basically 9a square px square का square root lambda of p is equal to. Somehow if the overall sign problem is solved, I simply get lambda of p is equal to 3ap, which means it is a, because square roots of px square will become p, so it gives me a linear dispersion. And that is what your Dirac dispersion is. So you need to end up getting some kind of a linear dispersion. Dirac dispersion, Dirac fermions, massless Dirac fermions have a linear dispersion. So what we are trying to say is that at these Dirac points, which are these k plus and k minus points, where is, yeah, for at these k plus and k minus points, the dispersion, the two bands touch each other, and near these Dirac points, your electrons behave like Dirac fermions, massless Dirac fermions, which means your electrons behave like massless particles, and they have a massless kind of a dispersion. They have a photon kind of a dispersion. So that is what you see when you do this expansion, when you do this k plus, when you do this expansion around k plus, this is what you end up seeing. But yeah, so this sign problem is a little bit of a hassle. I'm not sure how to deal with this sign problem here, because this should not have appeared ideally. I made a small calculation error somewhere. Um, that should ideally solve this sign problem. Okay, but that one single sign problem aside, you get the overall idea that when you expand it around k plus and k minus, this is what you end up getting. You end up getting a linear dispersion. Normally, okay, let's compare it with the normal dispersion you get. If I had a normal free particle electron, my dispersion would look something like p square by 2m, correct? Which is a parabolic dispersion. Oh, that's a bad way to show it, but yeah, this is a parabolic dispersion, right? I have, let's say, some mod p here, and I have lambda or energy, whatever, and it's a parabolic dispersion. But in this case, in this particular case, near the Dirac nodes in graphene, in a system as simple as graphene, which is just carbon atoms, near the Dirac nodes, you end up getting a dispersion like this. This is my mod P, and this is my energy, or I can say that this is Px also, and this is my energy. So I end up getting a linear dispersion, and you know that E is equal to h nu for photons, right? So E is equal to hc by lambda for photons. And what is the momentum relation for photons? How do you calculate momentum? P is equal to h by lambda for photons. So therefore E becomes Pc. Here you can see E is equal to P square by 2m. For photons, E is equal to P into C. So for photons, you get a linear dispersion. For normal particles with mass, you always get a quadratic dispersion in nature, in free space. But inside your condensed matter system, the interactions are arranging itself such that your electron near these Dirac nodes behaves like a massless particle. So that's such a interesting thing that comes out. Okay, so this is the first problem. So this is how you're supposed to write down the tight binding structure, and you have to find the nature of the dispersion in the vicinity of Dirac points. Okay. Now let's try to solve another problem which is not in your assignment. This is given in your assignment, so there are other steps also, like what is the Fermi velocity and all, so you can do it by yourself. But let's do a new problem now. I hope there are no doubts here. I'm actually not even waiting for asking doubts anymore, because you guys don't interact. If someone's unmuting and asking me questions, I would love to interact, but I don't see any kind of interaction from your side. Are there any doubts in this? Okay then. Okay, Aritra. All right. Yeah, so let's move on to the next kind of problem. Next, I would want to look at the Jordan-Wigner transformation. So what does Jordan-Wigner transformation do? Normally, it is very difficult to deal with spins or fully solve a spin system in condensed matter physics. But what does Jordan-Wigner transformation do? It for a simple non-interacting Hamiltonian, for a normal non-interacting spin Hamiltonian, it can simply transform it into a fermionic Hamiltonian. Okay, so you can transform the operators such that the Hamiltonian can be written in terms of fermionic operators. And solving a non-interacting fermion problem is simple as compared to a non-interacting spin problem. So Jordan-Wigner transformation actually helps you do that convert your spin Hamiltonian to a fermionic Hamiltonian. But how do you do that? So for that, there are certain steps that you have to take. Firstly, so for a single spin, if you don't have a spin chain, but you just have only one spin, so you can directly say that an upspin behaves like a filled particle and a downspin behaves like a vacuum or no particle. Okay, so here there is a direct correlation between a fermionic operator and spin operators. And similarly, you can write down Sz and Sx and Sy, all of these operators. You can write Sz, Sx and Sy, all operators in this manner. Let me just copy this and write it down. This is for a single spin. Please try and remember. Please try and understand what we're doing. Let's not get confused. For a single spin, there is a direct correlation between upspin and filled particle and downspin and a vacuum. And so we write down the operators Sz, Sx and Sy in terms of these fermionic operators itself. Sz, which is just this kind of an outer product, can be written as f dagger f minus half, and Sx can be written as this, which directly corresponds to this f dagger plus f. So Sx is simply f dagger plus f, and Sy is 1 by 2i f dagger minus f. Okay, so this is for a single spin. But now when you have many spins, when you have a spin chain, these relations don't hold true. So Jordan Wigner concocted up or came up with a very interesting transformation which can work in a spin chain as well. And that is the next step that you take. For a single spin, maybe I'll just even copy down these relations. Okay, so for a single spin, even these relations are satisfied, which you can write in this relation you can write in terms of Pauli matrices or in terms of spin operators directly. And there is also an anti-commutation relation of this sort which is followed by these spin operators. Okay, now this section is separate, so let's separate it out. From here, this is for spin chain. Okay, from here the entire section is for spin chains. For spin chains or many spins in general. A spin lattice kind of a thing. Okay, from here it's for many spins. So the transformation that Jordan Wigner came up with was this, that the creation operator at Sj, so Sj dagger, can be written as Fj dagger with e raised to power I phi j. So you have learned this in your class as well. Sir has taught you this, that Fj dagger e raised to power I phi j. What is phi? Phi j is simply pi into sum of all the occupation numbers till that spin. Okay, so if I am thinking of a spin chain, okay, and I equals, let's say this is j, so let's say j equals 4, so phi j, phi 4 is what? Pi into sum over L less than j. So till here I will go from I equal to 1, 2, 3. I'll go at 1, 2 and 3 and check whether the spins are present or not. I'll check whether the occupation number is 0 or 1, whether the lattice point is occupied or not. Okay, so let's say I equal to 1. I can see that this point is occupied. So I will write 1 plus, this point is also occupied, this point is also occupied. So 1 plus 1 plus 1. That gives me 3 pi. If one of these spins is not occupied, in that case I would have gotten a 2 pi, let's say. Understood? So this is how you write a string phase. This is something called a string phase, and that's how you write a string phase. Right, so just by doing this transformation in your creation and annihilation operators, what you end up getting is a proper fermionic relation between your operators. So now Sj is written exactly as it was being written previously, because the phase factors cancel out. So Sz is still Sz, but S plus and S minus have this string phase factor. They come with this string phase factor, and this string phase factor has certain properties. So this string phase factor actually satisfies this kind of these kinds of anti-commutation relations, both of these. It satisfies these kinds of anti-commutation relations. How do you check whether it satisfies these anti-commutation relations or not? So if I write e power I pi nj fj plus fj e power I pi nj. So what is this equal to? Let's say that the site j is occupied. Basically, if I operate nj at site at my state, I get 1, which means the site j is occupied, right? So in that case, what do I end up getting? What I end up getting is nj e power I pi nj. Nj means the occupation number at j, so that is 1. So this has a minus sign, this has a negative sign, because e power I pi nj is 1. So e power I pi, which means minus 1. So this would become minus 1 in that case. And fj first operating on that state will destroy the particle in j. So then this gives me 1. Right? So what I end up getting is fj minus fj is equal to 0. So what I did is, when the state j is occupied, the phase factors give me different values. The phase factor on the right gives me minus 1. The phase factor when it's on the left, it gives me plus 1. So it gives me fj minus fj, and that gives me 0. The net value comes out to be 0. Okay. Now suppose the state is unoccupied. What happens then? If the state is unoccupied, then this becomes plus 1 because nj is 0, but fj destroys the state, so that gives me 0. Again fj destroys the state, so that gives me 0. So again I end up getting 0. So what I'm trying to say here is that this anti-commutation relation is satisfied. This anti-commutation relation is satisfied. Okay, similarly you can give arguments of a similar nature and calculate the anti-commutation relation of this form as well. Okay, I think there is something else as well. Is there another kind of anti-commutation relation? Wait. Oh, right. So I need to even check whether okay. Now let's calculate a few anti-commutation relation, and finally what we want to do, what we aim to do with this is write another spin Hamiltonian, not the one taught in class, but something else, a new spin Hamiltonian using these fermionic operators. Okay, so check whether we can. So the first step is check whether these other anti-commutation relations are also satisfied, and then proceed to writing that Hamiltonian. Okay. where L is less than J, and now again e raised to power I phi j FL dagger equal to 0 when L is greater than or equal to J. Sorry, this is not an anti-commutation relation, this is a commutation relation. हाँ मामा, मारो मारो लेक्चर चल रहा है, बोलो बोलो बोलो. हाँ 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 ना तो આપણે ગાડીમાં જઈએ. हाँ हाँ ओके ओके. Okay, so basically we have to check whether these kinds of commutation and anti-commutation relations are satisfied. Okay, so let's check. How do I check this one? E raised to power I phi j FL dagger plus FL dagger e raised to power I phi j. What do I end up getting here? So if L is less than J, okay, if L is less than J, phi j, it means that you have a phase. Phi j is what? Is equal to pi sum over NL, where L is less than J, correct? So if L is less than J, which means here let me assume that site L was unoccupied initially. Okay, let me assume that site L was unoccupied. Then when I calculate this, what I get is FL dagger, and this has e raised to power I pi into other numbers less than J and K not equal to L, and it also has e raised to power I pi, and because L is not occupied, this gives me a 0 here, right? Plus there is an FL dagger here, and this e raised to power I phi j, here it becomes e power I pi sum over nk k less than J. I don't have to separate this out because this won't be 0 anymore, but nonetheless let me separate out for clarity. Multiplied by e raised to power I pi, I'll have another e raised to power I pi here, because the L state is now occupied, so that NL will be 1, and that will give me additional phase factor of e raised to power I pi. The phase difference between these two terms will be e raised to power I pi, whatever state I am in. Whatever I start with, there will be a phase difference of e raised to power I pi. Okay, so what that ends up giving me is e raised to power I pi sum over nk k less than J, k not equal to L, that's outside, FL dagger minus, sorry, I'll have a minus FL dagger plus FL dagger, that gives me 0. So now I can see that this anti-commutation relation is clearly satisfied. Similarly, if L is greater than or equal to J, then I have to show that this commutation relation is satisfied. Second is e raised to power I phi j comma FL dagger, that is equal to e raised to power I phi j FL dagger minus FL dagger e raised to power I phi j, right? So since now this is for L greater than equal to J, since phi j is independent of whether the state L is occupied or not. Since phi j is independent of whether the state L is occupied or not, e raised to power I phi j will remain the same and it can come outside. So I have FL dagger minus FL dagger, that gives me 0. So the second commutation relation is satisfied like this. The first anti-commutation relation is also satisfied, second commutation relation is also satisfied. Okay. Now that we understand how to use this string phase and do certain kinds of manipulations, let's try to write a particular kind of a Hamiltonian. Okay, so I'm basically using the book Peirce-Coleman, and I'm solving a problem in the book Peirce and Coleman. Okay, so there is a Hamiltonian. It's called the transverse 1D transverse field Ising model. Okay, so the Hamiltonian looks like this: minus j sum over small j sx j sx j plus 1 minus h sum over sz j. So this is your transverse field 1D Ising model. Okay, so basically it started with these terms being sz and this term being sx, and they have done some kind of a rotation which you can perform. You rotate basically all of your spin vectors so that you can get a desired direction. So that's how you end up with this kind of a Hamiltonian. Just saying this because if you look at transverse field 1D Ising model and you don't see this kind of structure, you might get confused. So I'm just telling you that it starts with sz here. It's sz j plus 1, and this is sx. It starts with this, and then you perform certain kinds of rotation on the operators. I am not going into those details because that's not relevant. What we want to do is just use Jordan-Wigner transformation here. Okay, so what is sxj is simply s plus s minus j plus 1 by 2. Therefore, when I write it in terms of fermionic operators that we have, what do I write s plus as? I write s plus as this, sj plus as this. Fj plus e raised to power I phi j plus Fj e raised to power minus I phi j that's s minus, right? Fj e raised to power minus I phi j divided by 2, and sx j plus 1 equals f j plus 1 dagger e raised to power I phi j plus 1 plus f j plus 1 e raised to power minus I phi j plus 1 divided by 2. So now you're supposed to multiply these two to get the Hamiltonian. And sz also, we already know what that looks like: fj dagger fj minus half. So we're not concerned with that much. Let's try and write the whole Hamiltonian. So sx j plus 1. What does that give me? It gives me fj dagger e raised to power I phi j. Let me take 1 by 4 outside as common, plus fj e raised to power minus I phi j multiplied by f dagger j plus 1 e raised to power I phi j plus 1 plus f j plus 1 e raised to power minus I phi j plus 1. Alright, You have a capital J outside, which I forgot conveniently. Right. So now I have to multiply these operators and see what I end up getting. Sorry. Okay, so now I have to multiply these operators. So now this is equal to, let's say, j by 4. Fj dagger e raised to power I phi j, Fj plus 1 dagger e raised to power I phi j plus 1. Wait, do I have a Hermitian conjugate as well in this? No, I don't. So these are the only terms, right? So what will this give me? Phi j plus 1, F dagger j plus 1. Plus second term is F dagger j e raised to power I phi j, F j plus 1 is I phi j plus 1. Okay, so what I understand from here obviously is that e power I phi j and F j plus 1 dagger, these two can commute, as we have already seen this relation here. E raised to power I phi j and F L dagger, because L is greater than j, these two can commute and there won't be any issue, right? So actually let's do term by term, let's not complicate this. So I will just take one term first. I'm taking only F j dagger e raised to power I phi j, F j plus 1 dagger e raised to power I phi j plus 1. Okay, and for this term what I end up doing is F j dagger F j plus 1 dagger e raised to power I phi j e raised to power I phi j plus 1. Okay, so because these terms commute, so this is what ended up happening, and now I have F j dagger F j plus 1 dagger e raised to power 2 I phi j, because till phi j the entire phase repeats, so I can simply add those two into e raised to power I n j, I pi n j, sorry, n j plus 1. So only the j plus 1 now remains isolated, otherwise everything up till j has been repeated. No, actually it's nj only, not nj plus 1, because L is less than j. Yeah, so this becomes double and 2i and some number 0 or 1, 2i pi and some number 0 or 1, which tells me that this is strictly 1. So therefore what this term ends up becoming is fj dagger fj plus 1 dagger e raised to power I pi nj. Let's look at the second term. The second term is, this is my first term. The second term is j dagger e raised to power I phi j, f j plus 1 e raised to power minus I phi j plus 1. There is a phase with a negative sign, right? So for this term, again, these two can commute with each other. So that's why I get fj dagger fj plus 1 e raised to power I phi j e raised to power minus I phi j plus 1 equals fj dagger fj plus 1. Till phi j, my phase gets cancelled off, and what I end up having is e raised to power minus I pi n j. Right, that's my second term. Now let's look at the third term. fj e raised to power minus I phi j, fj e raised to power minus I phi j, fj plus 1 dagger e raised to power phi j plus 1, fj plus 1 dagger e raised to power I phi j plus 1. Again, this phase commutes, therefore fj plus 1 dagger e raised to the power of I pi n j, fourth term. fj e raised to power minus I phi j, fj plus 1 e raised to power minus I phi j plus 1. That again gives me fj plus 1 e raised to the power of minus I pi n j. Okay, so um, so let's say if, let me think of cases. Let's say if nj is equal to 1, then what happens? If nj is already occupied, then I get fj dagger fj plus 1 dagger here with nj 1, which is minus, but fj dagger will make it 0, so this term goes away if nj is 1. Again, this term also goes away if nj is 1, but this term and this term survives, and what I end up getting is fj plus 1 dagger, nj is 1, so minus, and fj plus 1. So it's basically fj into fj plus 1 minus fj plus 1 dagger. If nj equals 0, what that gives me is, if nj equal to 0, then in that case this is fj dagger fj plus 1 dagger. If nj equal to 0, this is fj dagger fj plus 1. And these two become 0, last two terms. That is fj dagger fj plus 1. fj dagger fj plus 1 dagger plus fj dagger fj plus 1. So how am I supposed to write this in a more general fashion, in the most general manner? This nj does make sense, that's nothing wrong here, but this has to give me some general term, no? NJ occupation, and this has a very clear cut relation. So what I realize is that this term always has to have e power minus I pi nj1 nj0, then this term anyway won't be there. So let's say this fj plus 1 will always be accompanied with a negative sign. Oh, I think I didn't have a negative sign here, but it will always be accompanied with a negative sign. What about this? This will always be accompanied with a negative sign, fj plus 1 dagger, because it's nj. So if nj is 1, if nj is 0, then this is anyway 0. If nj is 1, then this will always be accompanied with negative sign. What about this? Here I'll require nj0, so fj dagger fj plus 1. This will always be positive as a sign, and this will also always have to be positive, j dagger fj plus 1 dagger. So fj so basically what I have is I think that makes, yeah, so I have my fj will always be accompanied with a negative sign. Yes, that's perfect, I think. Fj dagger minus fj into fj plus 1 dagger plus fj plus 1. These are the 4 terms, minus j by 4. So I'll just explain what I did. Let me erase all of this. Let me erase this. Okay, So now my first term, which I was considering, so first term has fj dagger. Okay, now if nj equal to 0, then only this term will be non-zero firstly, because otherwise if nj equal to 1, fj dagger will kill it because it's the fermion operator, right? So nj has to be equal to 0. nj 1 means the term itself becomes 0. So when nj equal to 1, then clearly this, sorry, when nj equal to 0, it has to be nj equal to 0. So when nj equal to 0, this term gives me 1. So this operator will always have this form, fj dagger, fj plus 1 dagger. I don't need to know the occupation of nj, because if nj is a 1, then this term anyway uh, destroys the state and it gives me 0. So this term itself destroys the state, so I don't need the phase factor. And when nj equal to 0, the phase factor accounts to 1. So this is my term. The first term becomes this. What does the second term become? In a very similar manner, the second term also becomes fj dagger, fj plus 1. You can check this. When nj equal to 0, only then this term is non-zero. Oh, I need to attach. Only then this term is non-zero. When nj equal to 1, this term becomes 0. So I don't need to bother with that. So yeah, that's my second term. In my third term, nj here, for this term, nj has to be equal to 1. 0 won't suffice. 0 won't. Nj equal to 0 will give me, the term itself will give me 0. So it will always have a negative sign when nj equals 1. Again, when nj equals 1 here, even this term will always give me a negative sign. So this term always ends up giving me fj plus 1. So what I have is 4 terms like this. I don't need to take cases. I simply have 4 terms like this. First term is fj dagger, fj plus 1 dagger. Second term is fj dagger, fj plus 1, fj dagger, fj plus 1, minus the third term is fj, fj plus 1 dagger, and the fourth term is fj, fj plus 1. So I'll combine this. Fj plus 1 is on the right. I can't combine like that. Fj dagger minus fj into fj plus 1. That's 2 terms, and the other 2 terms are plus fj dagger minus fj, again that, to fj plus 1 dagger. So therefore what I end up getting is fj dagger minus fj into fj plus 1 plus f dagger of j plus 1. This is what I have written here. That's the term I end up getting with a negative sign outside. I can remove the negative sign and simply write it as fj minus fj dagger into fj plus 1 dagger plus fj plus 1. And the sz term also, I know that it is plus fj dagger fj minus half is just a constant shift in energy, so I can remove that. So this is the final answer. Let me check, and yeah, this is what I end up getting. There is a minus sign, of course, because the Hamilton itself has a minus sign. Minus h. So that's why here also I'll have a minus h, fj dagger fj. Alright. So this is what we end up getting. So this is how we write it down, and then yeah, you can simply transform it to the momentum space and get the energy eigenvalues, etc. That's a standard similar procedure, but just that how to write this is what I wanted to show. So yeah, that's your problem number 2. Okay. If I look at your assignment, in that problem number 1 is something that I very closely followed. Problem number 2 is simply free particle Green's function in the momentum space. You know, free particle Green's function looks like g of k comma omega is what 1 upon e raised to power omega minus ek plus I eta. Correct? So these are your terms in your free particle Green's function in the k and omega space, in k and momentum and omega space. So what are these individual terms? This is just the energy of the particle. This is the dispersion relation, and I eta, you know what I eta is. I eta is that damping factor, or the factor that you add so that your integral does not diverge. So that is in a way a damping factor, or yeah, you can have some physical interpretations also of this factor. So there is some physical interpretation, you can use that as well, but yeah, this is some kind of factor which helps your integral converge. So that's what you are supposed to write down. What do all these individual terms mean? Question number 3 is the Fourier transform. You can simply do the Fourier transform. It's a very standard Fourier transform in the r theta phi space. It's a very standard Fourier transform, the r theta phi space. If you look at any standard math textbook, you can find this Coulomb potential ka. This is something called Yukawa potential because it's a screened Coulomb potential. So you can find a derivation of Yukawa potential ka Fourier transform. That's a very standard problem. Problem 4 and 5 are from week 3. So we'll look at them or problems similar to that in the next week. So I think we can end the session here. If there are any doubts, we can open the session for doubts now, or else we can just end this right here. Are there doubts?
Sir, I have a question on the assignment.
On the what one? What?
About assignment. In some question of assignment.
Okay. Tell me what question of assignment you have doubt.
In the week 0 assignment, there is some question that says read something. So read Bloch's theorem, read band theory of solid. So that is question, or that that is my prerequisite.
I think Mr. Shah, what he's trying to say, I had the same query as well as him.
Yeah, I could see that.
Is that whether we have to write out the read questions? For example, I'll give you an example. In the assignment 0 PDF, we have the 7th question as read Bloch's theorem, chronic Penny model, and band theory of solids.
Right.
So when I'm submitting that assignment, do I have to write out all of this question with all the theory, or should I attempt only the direct questions, such as what is Hall effect, what information does it give?
No, you don't need to write down the read questions. Obviously, basically, the prerequisite assignment is meant to check your knowledge. So because you can see that now I directly go into the tight binding model for the second quantization. So if you don't know the tight binding model, basics of tight binding model, understanding it from the perspective of second quantization becomes like one step added difficulty. So that is why it's recommended that you should know all of this. Okay, so
got it.
Yeah, so you don't need to write down anything for the read questions.
All right, thank you, Mr. Shah.
Yeah. All right, is there anything else? So basically, guys, if at all you are lagging behind in the lectures, and maybe see, I'll be taking my classes week to week. So if you're lagging behind in the lectures and you still have doubt later when you go through those lectures, there is a discussion forum. Please use that. So in the discussion forum, you can just go around, you can just go ahead and ask your questions, and either the professor or me, either of us will be answering those questions. So that would give you a much better insight. Like anyway, you don't have any live interaction. Maybe there will be a live interaction session with professor as well. There will be 1 or 2 live interaction sessions with him. But in spite of that, you can just go ahead and ask your questions, and he can answer those on the discussion forum, and others also can read, so they also can add their knowledge. So yeah, that's it. You can of course come on this session and ask me live, or you can ask in the discussion forum as well. Okay, all right then, let's end this session today. Thank you so much for attending. Yeah, bye.